फिक्र उम्मत की फिक्र हर इंसान को नहीं है, इसलिए हर इंसान इकबाल को नहीं समझा सकता। इकबाल खुद कहता है जी।
बता रहा हूँ।
Okay, so Assalamu alaikum and welcome everyone to the online lecture series by the Khwarizmi Science Society. We're sorry for the slight delay today and we're going to begin shortly. Over to Dr. Sabina.
Right, and Assalamu alaikum everyone, and thanks for joining in the fifth session of this Khwarizmi Science Society lecture series. May I request everyone to please mute their microphone so that we could start. All right, so we are recording this session again, and we would like to share the screen. All right, so how's everything going today? I hope everything is fine at your end. So far, we've talked about quantum states. So a quick recap of what we've done. We've discussed quantum states. Am I perfectly audible to everyone? Can you hear me properly?
Yes, sir, it's fine.
Okay. So we've discussed quantum states and how to represent those states. Then we've also talked about quantum gates. We've seen quantum algorithms. Actually, we've just seen one algorithm, which is the Deutsch algorithm, but that is quite representative, and that's the simplest of algorithms that we could ever discuss with a quantum computer. And we've also, on the sidelines, talked about measurement, as well as an archetypal quantum interference experiment. So these are all the ideas that we've covered so far. And I hope that these ideas do start making some sense to you. So before we begin today's lecture, which is going to discuss today's lecture, which is basically going to introduce the concept of quantum entanglement. I would just like to pause here for a few moments and take up any questions or suggestions or comments about the topics that we've covered so far. So let's pause for a few minutes and see if there are any outstanding questions before we move ahead with entanglement. All right, so any questions, any thoughts, or should I just move on?
Doctor, I have a question.
Yes, please.
I didn't exactly understand what is the use of the ancillary qubit. Can you explain that again?
All right, so in the Deutsch algorithm, what we wanted to do was we have two inputs, 0 and 1. Okay, and what we wanted to do was to find out whether a function f, which acts on either 0 and 1 and takes it to 0 and 1 in some manner, we'd like to look at a property of that function. And the promise that we are given is that this function f is one of two kinds. It is either constant or balanced, which means that we need to evaluate f of 0 and, look at this word, and we need to evaluate f of 1. So if I had a quantum computer, and what I could simply do is I could input ket 0, have a function u of f, which gives me an output f of 0, right? So I could easily compute the function acting on ket 0 through this quantum computer. But I need to know a property of the function, which means that I will perform another experiment. So this is in black, I show my first experiment. In green, I show my second experiment. I reinitialize the experiment such that I now input the quantum state ket1 into the same function, and I find out what the output is. Then I would like to compare this output, the black output, with the green output, which means I would like to compare the outputs of the two functions. So I have one qubit coming in, one qubit going out. I could easily do that, but that does not reveal the power of a quantum computer. In a quantum computer, you would like to do both of these experiments in one go. So what you were interested in is that you make a 2-qubit quantum computer in which the first qubit is your qubit of interest and the second qubit is an ancillary qubit, which you initialize somehow. And in the first qubit, path of the first qubit, you add some operation, something u1, and then you apply your function onto the ancillary qubit. And then after you've gone through the black box, the uf, you do something to the first qubit, you could do something to the second qubit, and then you just throw away your ancillary qubit, which means you don't care about it, or it is left in a state, a final state, which is the same as the initial state. And lo and behold, here, if you were to perform a measurement on the first qubit, some kind of measurement, by looking at the classical output of this measurement, that is whether this channel clicks or this channel clicks, you can look at the property of the function f itself. And the ancillary qubit you required to make the quantum computer work. So it's essential for the quantum computer, but at the end of the computation, it's just left in the initial state. So in chemical reactions, you are generally accustomed to the idea of catalysts. The catalysts are needed for the reaction to be catalyzed or accelerated, but they are not consumed in the process. So it's like a quantum catalyst. The ancillary qubit is required to implement your algorithm, but at the end of the day, it's the working qubit or your qubit of interest that carries the result itself. It's also possible that your first qubit becomes the ancillary qubit at the end of the computation, and your result is encoded into the original ancillary qubit. So you have a swapping of roles between the ancillary and the working qubits. So I hope this clarifies the idea of an ancillary qubit.
Yes, thank you, Doctor.
Okay, and we'll look at one more example today. So don't you worry about it. All right, so any more questions? So we'll just proceed. So let me ask a question now. Suppose I have a 2-qubit state ket 0 tensored with ket 0. Now In shorthand, I could write this as 0, 0. Now, what if I would like to make a state ket 0, 1 plus ket 0, 0 over under root 2? Or let me write this in this fashion. So I need to do a transformation, some logic gate, which takes this input and gives me this output. So what kind of quantum circuit can I draw? So I'm asking this question, it's over to you. What kind of logic gates or quantum network should I draw that can achieve this output?
Hadamard gate.
On which qubit?
On second qubit.
On the second qubit, exactly. So I do nothing to the first qubit, and on the second qubit, I put a Hadamard gate. So if this is my quantum computer, this thing here, this is my quantum computer. And I input ket 0 crossed with ket 0. This output is exactly going to be what I've written over there. So what I put in orange is a quantum transformer or a quantum gate. I do nothing to the first qubit and I put a Hadamard gate on the second qubit. So if I would like to write a matrix for what I've written in orange, I could write this in the following form. I do nothing to the first qubit, so I just put an identity matrix and I put the identity matrix in a bold 1. So it's different from the number 1. Each matrix that acts on a qubit has to be of the size 2 by 2. And I take the tensor product of this matrix with the Hadamard matrix, which we've already seen. So this is the unitary operator on which is drawn in orange. So it's also a quantum gate. It does nothing to the first qubit and applies or implements a Hadamard gate on the second qubit. So if I were to write a matrix for this, this would be simply the identity matrix tensored with the Hadamard matrix. Okay, and this turns out to be 1 over under root 2. I first take the number 1 and multiply it out with the matrix, which becomes 1, 1, 1 minus 1. Then I would take 0 in the same order. I would repeat 1, 1, 1 minus 1. So this is the matrix for the unitary transformation on the 2-qubit state. And you could verify that your output is the desired output by encoding your input state as 1, 0, 0, 0. And your output will of course be equal to, here it's going to be equal to 1 over under root 2 1 1 0 0. You can verify this, or so this is like a homework problem. All right, so the output state, if you observe, let me rewrite the output state. Ket 0 0 plus ket 0 1. So this output state is really that nothing happens to the first qubit, but the second qubit is converted into a superposition, an equal superposition of ket 0 and 1. So if you look at the output state, I can also write this as a pure quantum state on the first qubit and a pure state on the second qubit. This is what I could write. Agreed? So this makes sense, okay?
Doctor,
Yes, please.
why we can't put the Hadamard gate on the first?
No, you can if you want, but what I desire, this is my desire here. I desire or I wish to produce this output state. So if I put the Hadamard gate on the first qubit, I wouldn't get the desired state. Instead, I would get 0 0 plus 1
1
0
0.
over.
Yeah,
Okay.
yeah, yeah.
So So that is not what I desire, what I wish. Okay. All right. So if you observe this state here, this output state, I can factorize the state. You know the word factorization. Factorization normally means if I write 12, I can factorize this as a product of 3 and 4. But this quantum state is also factorizable, not in the mathematical sense, but in the quantum sense, which means that I can write the identity of the first qubit and the identity of the second qubit separately. So the first qubit could be in some state chi, and the second qubit could be in some state psi. Each one of them is normalized, and I take the tensor product of two. So I can decompose my overall state. This can be an overall 2-qubit state, right? So I put a 2 on top of it, indicating it's a 2-qubit quantum state. And this 2-qubit quantum state has been separated out or factorized out into chi and psi. So this is an example of what is called a separable state. Now let me pose a question. And the question that I would like to pose is the following. Suppose I have an input state cat0 crossed with cat0, and I put a Hadamard gate UH on the first qubit, and then I do a controlled NOT operation. Okay, in which the first qubit is the control qubit and the second qubit is the target qubit. Now I give you 2 or 3 minutes. Can you work out the output state? What is the state that we will achieve at the output? Just on your paper, take 2 or 3 minutes and please provide an answer. You can speak up, but don't speak up earlier than 1 minute, because I would like everyone to perform this calculation. So after a minute or so, you're welcome to speak up. So I give you 1 minute, please. All right, so you're welcome to provide an answer. Anyone?
Can I answer, please?
Yes, please.
Kit 00
Yes.
plus Kit 11 over root 2.
Excellent. So who was this? What's your name?
Sajida Habbush.
Sajida Abush. This is exactly the correct answer. So I could go step by step. So what we could have at this stage, we can have a state which is 0 plus 1 over under root 2 tensored with ket 0, which is 0, 0 plus 1, 0 over under root 2. And then at this stage, at the final stage, we have a controlled NOT operation. And if we look here, this ket 0, 0, because of linearity, remains 0, 0, whereas 1, 0 becomes 1, 1. Now this state that I've written in orange, the output from the drawn quantum circuit, is this separable? The question is this a separable quantum state? can I factorize this quantum state into a state on the first qubit separately, independently from the state of the second qubit?
I think no.
No, you cannot. Exactly. You can never express this as something on the first qubit and something on the second qubit. So you can't write this in this form. Okay. Hence, this is an example of what is called an entangled state. An entangled state is not a separable state. It cannot be factorized into something on the first qubit and something on the second qubit. So with 2 qubits, can you state the kind of entangled states that we can write? We already have looked at one of them, 0, 0 plus 1, 1. Could you give me another example?
So 0, 0 minus 1, 1.
Exactly.
Dr. Sabi, I have a question.
Yes.
For instance,
So
there is
let's
0,
first finish.
0. Okay, sorry.
Bilal, let's first finish this. Then ask me.
Sure.
Any more examples? Any more example of a state for 2 qubits that you cannot write as a factorizable product of 2 qubits?
1, 1 minus 0, 0.
So if you write 1, 1 minus 0, 0, then this is just the same as this state. They are just the same. There's just a global phase factor which connects these states. So this, if I put a minus sign here, which is e raised to power minus I pi or e raised to power I pi, I would get the same state. So the state that you propose is not different from the state that I've written on the left. Any more examples? Or we just exhausted all?
How about 1, 0 plus 0, 1?
Exactly. Umar Abu Taha, this is perfectly correct. And one last example. Sorry, 0, 1 plus 1, 0. One last example would be 0, 1 minus 1, 0. Okay. So these 4 states are called Bell states. And they are maximally entangled. The degree of entanglement for 2 qubits is maximal in these Bell states. And generally they are represented by phi plus, phi minus, psi plus, psi minus. Okay. So these are examples of 4 Bell states which represent maximally entangled states for 2 qubits. All right, Bilal, I can take your question.
Okay, sir. My question was actually related to entanglement and tensor products. So is my thought correct that with entanglement, you can't have tensor products? For example, we have cat 0, 0, cat 0, 1, 1, 0, and 1, 1. So since if we give the values like for 0 I have A and for 1 I have B. So if uh, with these values 0, 1 and 1, 0 can't exist, so that means that entanglement tensor products does not exist. Am I correct in that?
No, that is not the correct way of thinking about it. So let's
Okay.
look at the example of this state here. Okay, this is an entangled state and a Bell state. I cannot factorize this into something on the first qubit and something on the second qubit. If I expand this state and write it in a different form, this 0, 1, cat 0, 1 is basically 0 tensored with 1. Okay. And this thing is the second part of the superposition is cat 1 tensored with cat 0. Now, if I were to write this state alone, this is separable. And if I were to write this state alone, just on its own, it would be separable. Okay.
Oh,
But now
okay.
what I've done is I have a superposition of these states. Okay.
Oh, okay.
And then I do the normalization. So when I have the superposition, it is impossible to write this overall superposition state, which is a distinct state, perfectly legitimate quantum state, as something, anything on the first qubit tensored with anything on the second qubit. I can't do this.
Okay.
The mere act of superposition has converted this state into an entangled state. So it's a superposition of tensor products.
Oh, okay. The superposition was the key. Okay, I was missing that. Okay. Thank you, sir. Thank you.
All right. So if I look at this scheme here, these four states are maximally entangled, and I cannot factorize them into separable states. And look at this scheme here: a Hadamard gate on the first qubit, followed by a controlled NOT gate. So in order to prepare an entangled state, I need some kind of gate, which is the controlled NOT gate here, this gate here, this gate here. I need some kind of gate which correlates the two qubits. The Hadamard gate that I've drawn here is a local gate. This gate is local. It just acts on a single qubit. Whereas the other controlled NOT gate is a correlated gate, or it involves some interaction between the two qubits. So in order to prepare a Bell state or an entangled state, some kind of gate which is necessarily purely exclusive to qubit is required. A control NOT gate is an example. Now, one more thing, look at these four Bell states. If I were to go from phi plus to phi minus, so if I were fed in with a phi plus Bell state, and I would like to convert it into a phi minus state, how would I go about doing? What kind of circuit do I need for that? Okay, a simpler question. If I wanted to convert between phi plus and psi plus, what kind of gate is needed?
NOT gate on the second qubit.
Exactly. So this is the correct answer. If I take in phi plus and I do a NOT gate on the second qubit alone, I would get psi plus. So 0, 0 plus 1, 1 would become 0, 1 plus 1, 0. Now, going from one Bell state to another Bell state does not require an entangling gate or a correlated gate. A local gate will do. Likewise, if I were then allowed to put a phase gate here, a pi phase gate, and the truth table of the pi phase gate is that it does nothing to get 0, and 1 goes to minus 1, that is ei pi ket 1, which is minus 1. Then you will observe that this state will convert here. Here it's going to convert into 0, 1, minus 1, 0. Okay. And it's the same as minus 0, 1 plus 1, 0 because of the global phase factor. And then what I could do, I could apply a NOT gate here to the second qubit alone and convert this back into 0, 1, sorry, 0, 0, minus 1, 1. So just with the help of local gates, I can scramble between the 4 kinds of Bell states. But in order to create an entangled state in the first place, I would need what is called some kind of non-local gate. Okay, so I hope this is clear. Now, the other thing I would like to mention is, suppose I input cat 00, Hadamard gate, control NOT gate. Here, as you noticed, I get the Bell state 0, 0 plus 1, 1 over under root 2. What kind of circuit would I need to go back to? Okay, before I move on, suppose I do a measurement here. So now the counterintuitive aspect of entanglement comes to light. Suppose I'm talking about the polarization state of 2 photons here. I have 2 polarizing beam splitters, and I have a detector here and a detector here. So this is a 0 channel, whereas this is a 1 channel. Likewise, I have 2 detectors on the second qubit. This is a 0 channel and this is a 1 channel. So generally, when we talk about quantum computers and quantum information, one of the qubits belongs to one party, which we called Alice, and the other qubit belongs to another party, which we generally call Bob. So this is commonplace in quantum computing literature. Now, my question is that if I were to feed in cat 00 here at the orange region, I get the entangled state. What is the probability? And I'm looking at the 4 outputs. There are 4 outputs. Okay, there are 4 kinds of detectors in one go. Okay, what is the probability that I get 0, 0 as the output? So I would like to find out all the probabilities. I make a table. Can you help fill in this table for me? What's the probability that I get 0, 0 as my output? That is, the first Alice detects 0 and Bob detects 0. So P00 means that Alice detects cat 0 and Bob detects cat 0. So what is this probability? So Ran Gibrin says 1/2. Exactly. So this probability is 1/2. And what's the probability? What should I write over here? P11. One half. Exactly. And what are these probabilities? This and this. Each one of them is 0. Excellent. So look at this probability table here. If Alice detects cat 0, then Bob must also detect cat 0. And this is the property of the entangled state. If Alice detects cat 0 and Bob must also detect cat 0. So their classical outcomes, the results of their measurements, which are classical outputs, they are perfectly correlated. But it is also well nigh possible that Alice detects 1 and then Bob must also detect 1. If he were to perform simultaneous measurements, Alice and Bob, and then Alice and Bob were really, really far apart. One was on Earth, the other party was on Moon. So they have an entangled pair. Alice keeps one qubit in her pocket. Bob keeps his qubit in his pocket and moves to the moon. And then both of them have polarizing beam splitters and they measure their outputs. Then Bob makes a telephone call from the moon to Alice and tells his output and says it's 0. Then And then Alice would also look at her output and immediately reply that her output was also 0. And in the alternative scenario, if Bob mentions to Alice that his output is 1, then Alice looks at her output and she is surprised to find out that her output is also 1. Okay. And just another aspect of this really interesting phenomenon. So if I were to do the same experiment, Hadamard gate, controlled NOT gate, and this I just ignore. Okay, I put it in a trash bin. I don't perform any kind of measurement here. So I input cat 0, cat 0. I know what my orange state is. It's 0, 0 plus 1, 1. It's a Bell state. And Alice has a beam splitter, a detector detecting P0, and a detector registering P1. If I were to make a table just for Alice, so it will comprise 2 entries, P0 and P1, because I really don't care about what Bob sees. So I've just put a cross for Bob. It's irrelevant for Alice, for Alice or Bob, for the other party. So what is the probability that the first party, which Alice, gets a 0? So what's this probability here? What should I write here and what should I write here? Yes, please. So I'm not looking at the second qubit. I don't care what Bob does. I don't care whether he does an experiment or not. Alice performs her experiment. She'll either get a 0 or 1. But what are the probabilities of her getting a 0 and what is the probability of getting a 1?
Sir, everybody answered 1/2.
1/2. So, okay. Now, this is the really strange part. If Alice is looking at her qubit alone, she's getting a totally random output, perfectly random. Half of the times it's 0 and half of the times it's 1. So this is just a purely random event. Just like a coin toss. If the coin were fair, half of the times you would get heads and half of the times you would get tails. This is exactly what's happening in this scenario. But then if you were to perform the experiment together on the entangled pair of qubits, and Alice and both were to perform the experiment, even though each subsystem of the composite system, that is one qubit of the composite pair, even though each qubit alone, when looked at it alone, is behaving perfectly randomly. Sometimes a 1 comes as the output, sometimes a 0 comes at the output. But whenever the two results are compared from two random outputs, they are perfectly correlated. So this is really the strange thing about entanglement. And this idea is given the name non-locality. And tomorrow's lecture, I will look at the concept of non-locality from a purely mathematical perspective. But this, I hope, gives a fair idea of the power of entanglement. You have a composite system, each subsystem is acting randomly. Sometimes it's spitting out 0, sometimes it spits out 1. But then if the two random results are compared, they are perfectly correlated. So if I were to talk about coins and Alice, I'll take your question, Sajda, in a minute. So Alice and Bob, suppose they have two coins which are entangled, heads and tails. Now, if I ignore Bob for a minute and Alice were to perform her coin tosses, so sometimes you'd get heads, head, tail, head, tail, tail, head, head, tail, 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 head. So she'll get a random string of outputs. Okay. Now, if I don't ignore Bob, which means Bob performs his experiments, he would also get head, head, tail, tail, head, tail, head, and so on. So if Alice and Bob shared an entangled pair of coins, their outputs will be perfectly correlated. If you started off with this state, cat 0, 0 plus 1, 1. If you started off with the other state, 0, 1 plus 1, 0, with a positive or a minus sign, then the states would be perfectly anti-correlated, which is as good as correlation. So if Alice got a head, Bob would get a tail, head, head, tail, head, tail, which is equally surprising. So you have two subsystems that are acting randomly, just like random coin tosses. But when you compare the results of these two random outputs, you get perfect correlation. So this is a signature of entanglement, and it cannot be explained classically. It's a correlation which is far, far stronger than any classical correlation. And there are inequalities or tests that could be performed quantitatively to find out whether entanglement exists or not. So, Sajida, what's your question?
My question is why this correlation happen?
Okay, because if you have this entangled state and you perform a measurement of the kind that I've mentioned, okay, you have 4 detectors. So your possible outcomes are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so there are 4 possible outcomes. 0, 0 means that both Alice and Bob registered cat 0. 0, 1 means that Alice registers 0 and Bob registers 1. 1, 0 means that Alice registers 1 and Bob registers 0. Finally, 1, 1 means that Alice and Bob both register 1. Now, there are 4 possible outcomes with these 4 detectors. We would like to find out the probabilities of each. Now, quantum mechanically, how you would do that is you would take this state here. Let's call this phi plus. In order to calculate the probability of 0, 0, what you would like to do is you find the projection or the inner product of this Bell state phi plus with bra 0 tensored with bra 0. Okay, so you need to compute this. So this is the concept of inner product. So you need to project your Bell state onto your desired outcome, which is ket 0, ket 0. And when writing in a inner product form, these kets become bras. You know that. So if I were to perform this, I would write 0, bra 0, tensored with bra 0. Then I need to write the ket, which is now I'm going to reintroduce the tensor product sign, ket 0 tensored with ket 0 plus 1 tensored with ket 1. Okay, I've already written the 1 over under root 2. So if I were to perform this, remember that what I write in green belong to the Hilbert space of the first qubit. So the first qubit overlaps with the first qubit. So if I were to write the overlap for the first qubit, this will become 0, bra 0, ket 0, plus bra 0, ket 1. This is a number. Then I look at the second qubit. This thing, I need to find the overlap with the second qubit here and the second qubit here. And of course, I need to respect this positive sign, which is the linearity, 0, 1 plus 0, 0. So this becomes 1 over under root 2. This is 1. This is 0. This is 0. And this is 1. So I get 1 over under root 2. And then I take the square of this, because this is just a probability amplitude. I take the modulus square of this. I get 1/2, which is the probability that I've written over here. Okay, this probability. This probability also turns out to be 1/2, whereas these two probabilities turn out to be 0. As an example, what's the probability of projecting onto 0, 1? I just find this thing here. And you will notice that if I expand this, this becomes 0, tensored with 1. 0, 0 plus 1, 1. So immediately I find that if I were to take the tensor product of this bra 0 with this cat 1, I will get 0 as my output, and 0 when multiplied out with anything gives me 0 as the result. So I have 0 probability. So everything makes mathematical sense. In other words, I'm collapsing the Bell state onto 4 possible outcomes. 2 of them have 0 probability or 0 probability amplitude, and 2 of them have half the probability amplitude. Okay?
Thank you very much.
All right. So this is what I wanted to say about entanglement. Now, one last example I would like to give about entanglement is a full-fledged example of, I'll talk more about entanglement tomorrow, non-locality, and how do we test about non-locality, and what are the different nice things about entanglement, how we can put it to use. But quantum information or quantum states are really strange. First of all, the point that I would like to make is that you cannot copy quantum information. Copying is not allowed. In classical information, if I have a piece of paper and some information written on it, I can always take a picture of it and get another printout. I can copy information. I can put this into a photostat machine and I can copy information. But this is not possible for quantum states. I cannot copy or clone quantum states. So this is called the no cloning theorem in quantum mechanics. Now I can prove this or motivate this by a simple example. If cloning worked, then suppose cloning was true. Then if I were to take cat 0 and I had another qubit. So if I want to copy information, I need to have the qubit whose state I would like to copy. But copying means I would like to copy it onto another particle, onto another object, which is in an arbitrary state psi. So I need a kind of a scratch qubit. Scratch qubit, you can write something on it. So cloning means that this state cat 0 tensored with psi, which is arbitrary, becomes cat 0, right? So this is what cloning means. Okay. So I hope this is clear. So this second qubit is a scratch qubit. You can put information on it, and cloning would preserve the state of the first qubit. So in ideal cloning, the hypothetical cloning scenario that we're talking about, this operation that I've written here is possible. But if it were a perfect cloner, then my first qubit could also be in an orthogonal state cat 1. So if this were true, then 1 tensored with psi would go to 1 tensored with 1. So cloning should achieve this. So hypothetical cloner, quantum gate C, hypothetical. Now, if C existed, if such a gate existed really, then this should also be true. That is, if my initial state ket alpha, alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers. So I can just write this thing here, okay? So if alpha and beta are complex numbers, then I tensored it with an arbitrary state psi. If what I've written in the boxes is correct, so this, remember, this is simply alpha 0 tensored psi plus beta 1 tensored psi. Now, if cloning existed, if C existed, then by looking at the boxes that I've written at the top, my output state would be, so this would go into, because quantum mechanics is perfectly linear, alpha 0 0 plus, so this 0 is copied into the state psi, and similarly this 1 state is copied into this scratch qubit, just by dint of linearity, by virtue of linearity. So my cloner would give alpha 0 0 plus beta 1 1, right? So if 1 and 2 are correct, then this thing 3 will also be correct. 1 and 2 imply 3. If 1 and 2 are correct, then 3 is correct, because quantum mechanics, we all know, is linear. However, is this the last line that I've written, does this qualify as a cloner? Is this a cloning operation really? It's not a cloning operation. Not at all. It's not a cloning operation, because if this were a cloning operation, then my output state should have been the following. The state of the first qubit is alpha ket 0 plus beta ket 1. And what I should have achieved is alpha ket 0 plus beta ket 1. Nothing happens to the first qubit, and I copy the entire information onto the second qubit, which is alpha ket 0 plus beta ket 1. And this would have given me alpha square 0 0 plus alpha beta 0 1 plus beta alpha 1 0 plus beta square 1 1, which of course is not the same as 3. 4 and 3 are not the same. And for this reason, this is a proof or a motivation that cloning is not possible. Perfect quantum cloning is not possible. When we talk about quantum information, we can do approximate cloning, but nothing perfect is possible. So quantum information is really strange. By the way, there are other equally strange nuances or postulates about quantum information. First, let me give you another example. If I have something, some u something s, some unitary gate, and if I did not know what input state I'm feeding in here, psi, but I promise that this input state is of two kinds, either of two kinds. It could be one of ket 0 or ket 0 plus 1 over under root 2. So I promise that my input state ket psi is either of these two. Now, is it possible to tell in one experiment which of these possibilities is the input state in? So I'm asking whether I can perform a single experiment. I can design any US, or I can take a polarizing beam splitter. Can I distinguish between these two input states in a single experiment? Can I perform an experiment and tell what is my input state? Okay, Ran Jabreen, can you explain your answer? Can you unmute yourself? Is it possible for you to explain your answer? Or you can type here if you want.
Well, I have a mixed state and a pure state. If I were to create some form of matrix, a unitary matrix, that would change one of my pure states to a mixed state, or change my mixed state into a pure state, it will also affect the pure state, and I would still end up with, say, one of them including the other in a form or another. It would have, the first one has ket 0 and the other one has ket 0. Now, applying the matrix, because it's linear, it's going to affect the ket 0 in both of them. So I'm going to have a part of the second one that's going to give me sometimes the same result as the first one, so I won't be able to tell.
Exactly. So this is exactly the correct answer. So what Ram has been saying is that there is some ket 0 in the second possibility always. So if my output, suppose, turned out to be 0 in my first experiment, so this detector clicked, I cannot be sure whether my input state would get 0 or this state, because the second state also gives ket 0 as a possible output. In fact, it gives ket 0 with 50% probability. So in one experiment, I cannot tell. I could do another experiment, and still if I get ket 0, I still can't tell what my input state is. I would need to do an infinite number of experiments to distinguish between these states. Although the probabilities of getting ket 0, if I keep on getting ket 0s, the probabilities, I can have more confidence in one of the states, but still I cannot rule out the possibility of the input state being ket 0 plus 1 over under root 2. So your answer is perfectly correct. I just want to make one point clear, that both of these states are pure quantum states. And please don't use the word mixed quantum state, because mixed quantum state is totally different. Both of them are pure quantum states. The second state that I've written in a green box is also a pure quantum state from a quantum mechanical perspective. So this is terminology. A mixed state is something different. So it's a superposition. You can call it a superposition state or a quantumly parallel state, but it's not a mixed state. So in quantum mechanics, it's impossible to discriminate. Discriminate means to differentiate between non-orthogonal states. Okay, which means, by the way, that if I promised that my input were ket 0 or ket 1, and it's either one of them, then I could use a polarizing beam splitter. And then looking at the output, I can be sure what the input state is going to be. Okay, but ket 0 and ket 1 are orthogonal states. So I can have this polarizing beam splitter, which is projecting onto the orthogonal states. So one output channel is ket 0, the other is ket 1. So it's projecting onto the orthogonal states. And with such a device and with such a promise that I make about the input state, I can indeed discriminate between them. I can tell what is the input state. But in general, for non-orthogonal states, it is not possible. So I would like to finish off this lecture by giving you a small homework. You like to do it before the next class, which is tomorrow, and we'll discuss it in the next class as well. But what I would like you to think about is the following. I have an I have an arbitrary quantum state psi, arbitrary, totally arbitrary, which means it is some C naught cat 0 plus C1 cat 1, or alpha cat 0 plus beta cat 1. And what I would like to do is I would like to teleport this state. Okay. So what I am interested in doing is the following. I prepare this quantum state psi, and then I take 2 qubits. So I have a 3 qubit system now. And the property of these 2 qubits is that this pair of qubits is entangled, which means that this state is, suppose, a Bell state, 0, 0, plus 1, 1. So there are 3 qubits, qubit 1, qubit 2, and qubit 3. Let me write 2, 3, and 1 here. So qubit 2 and 3 are mutually entangled. They are entangled with each other. And then I give the first 2 qubits to Alice. Okay, I give these qubits to Alice. So Alice has 2 qubits now. One qubit has an arbitrary quantum state psi, unknown. Alpha and beta are not known. She does not know what alpha and beta are, because that's also impossible. And she has one qubit from within the entangled pair. And what she does is she takes her qubit and one qubit of the entangled pair and performs a control knot. Okay. And then she takes a Hadamard gate on the first qubit. And then what she does is she measures her qubits. So she has a polarizing beam splitter here. Suppose we're still talking about photons. So she has 2 detectors on the first qubit, 2 detectors on the second qubit, channel 0, channel 1, channel 0, channel 1. So the possibility of her outputs, there are 4 possible outputs. There are 4 possible outputs. Of course, Alice can detect 0, 0, or she can detect 0, 1, or 1, 0, 1, 1. Whereas the first output coming from the first qubit and the second output is coming from the second qubit, right? So you agree with me that there are, no matter what this circuit does, Alice can get 4 possible outputs: 0, 0, 0, 1, 1, 0, 1, 1. And once she has those outputs, these are just strings, 2-bit strings, 2-bit strings. Each string comprises 2 bits, and each bit can be 0 or 1. So she has 4 possible outcomes. Of course, with 0 and 1 and 2 bits in a string, you can have 4 possibilities, 2 raised power 2, 4 possibilities. Now what is happening in this circuit is that Bob, so the black box represents Alice, sorry, this dashed box represents Alice. But what Bob does is that he takes the second qubit of the entangled pair, which is the third qubit in our system, and walks away. Bob goes to another planet, he goes to a different country. Both of them, Alice and Bob, were in Jordan. They come to Pakistan or they go to the United States. So they become spatially separated. And what Alice does now is the following. She picks up the phone call. Alice picks up the phone. Right? And transmits the result. On a classical channel, on a phone line, she transmits her result to Bob. And she tells Bob whether she got a 00, or she got a 01, or she got a 10, or she got a 11. She tells her what of the 4 possibilities does she get, and informs Bob of the outcome. And what Bob does is that depending on what information he receives from Alice, he does some unitary gate on his qubit, right? Some unitary gate, which is, and there is a table, there is a correlation between what information he receives and what gate he needs to apply. And when he does that, this qubit psi is in the exactly the same quantum state as the original qubit number 1. So this is the concept of quantum teleportation. And it's only possible when we have an entangled pair. So what I would like you to do before the next class is to work out the quantum mechanics of this, work out the ket notation of this circuit, of this quantum network, this process, and show to me how is Bob's qubit an identical copy of the first qubit, and why does this circuit not violate the no cloning theorem? Previously, I mentioned that cloning is not possible. So does the teleportation circuit violate the no cloning theorem? And can information, quantum information in this case, be transmitted from Alice to Bob at just in an instant? Is this faster than light communication, which by special relativity is not allowed? So we would like to look at all of these questions, but at least I would request you to take this problem as a homework before the next class and work out what the quantum state is going to be for this 3 qubit system at various stages of the quantum network. All right, so we'll resume our next session tomorrow. So I'd be happy to take some questions now.
What's the unitary matrix of do?
Yeah, you have to tell me. You have to tell me what is the unitary matrix. So this is the question I would like to ask you. So depending upon the information Bob receives from Alice, he will have to apply one of 4 different kinds of unitary matrices. You like to tell me what are those unitary matrices? Okay.
Okay.
And write those matrices in matrix form as well. Of course, they are 2 by 2 matrices because this is just a single qubit in the possession of Bob. So please write down on your paper these matrices, and probably in the next class I will allow you to share your screen, and probably, or you could put the answer on a piece of paper on your computer and share your screen and share it with everyone. All right, so maximally entangled. There are possibilities of having states that are not maximally entangled as well. So, but that requires an understanding of mixed quantum states. We haven't covered mixed quantum states. So it's possible to have states that are not maximally entangled. Let me give you an example. Suppose I have 3 qubits. Okay. Now, if I were to write a 3-qubit state, I could write all right. Now remember, this 1 over under root 2 is still correct because probability needs to be conserved. 1 over under root 2 square plus 1 over under root 2 square is 1. Now this is a 3-qubit state. Is this entangled or not? Question. Is this an
Not
entangled state?
entangled.
Not entangled?
Mix between entangled and not entangled.
Exactly.
We
So
can
yeah.
separable one qubit, and that other two qubit we cannot separate it.
Exactly. So we can write this as ket 0 tensored with 0 0 plus 1 1. So I can separate out the first qubit from the second and third qubits, but I cannot separate out the second and third qubits. Okay. So this 3-qubit state, so if I were to represent this cartoonically, 3 parties, Alice, Bob, and Eve. First qubit, second qubit, third qubit. Qubit number 2 and 3, that is these qubits, they are entangled, but Alice's qubit is separable from Bob's and Eve's qubits. Okay, so this is an example of a non-maximally entangled state. Right, I think my my one pad has stopped working, so I'll have to restart this, but in the interest of time, not let's do that. So this is an example of a non-maximally entangled state. However, if I were to write the state 0 0 0 plus 1 1 1, this is an example of a maximally entangled state because everything is entangled with everything else. It is not possible to separate any qubit out or factorize any qubit out. So I can have states which are maximally entangled and states which are less than maximally entangled, which are imperfectly entangled or partially entangled or non-maximally entangled. So I hope I've answered your question here. Yeah, okay. And the concept comes more important when we discuss mixed states, but I haven't talked about mixed states. They are slightly more complicated for the level of this course. So we'll resume our discussion with teleportation tomorrow, and we'll also look at some non-locality tests, and we'll look at some really counterintuitive applications of quantum information. So with this, please try to attempt the homework. So that we can, so you have some work to do as well. So inshallah we'll meet tomorrow at 2 p.m. With the 6th lecture on non-locality. We'll continue with entanglement, and possibly I'll cover an example of quantum error correction as well. All right, so thank you very much, my friends. Thank you very much. Masalam.
Sir, wait a second. I think there's a question.
Yes,
Miss
please.
Ajda.
Yes, Sajda.
Can you repeat what we should in the homework? What we should do in the homework?
Yeah, I think you should, in the homework, what you should do is you should look at this example of teleportation and see how the quantum state progresses from one stage to the other. Like we did for the Deutsch algorithm, we wrote down the circuit, wrote down the quantum network, and saw how the quantum state progressed as we go from left to right in the quantum circuit. I would like you to do the same for the quantum teleportation circuit that I've drawn.
Okay.
Sir, I think there's this one last question by Sakura. She says that are there any advantages of no cloning?
No cloning is a disadvantage. You can't copy information. You would always like to copy information. So no cloning is like a limitation in quantum mechanics. So you have to go around it. In the example of teleportation, we are cloning information, but at the expense of destroying some qubits. And I'll explain that tomorrow. So it doesn't have an advantage. Rather, it puts constraints on us. It puts limitations on us. I can't think of any advantages of no cloning. All right. So if there are no more questions, so I'd like to thank you again, and inshallah, will see you tomorrow. Ma salam and Allah Hafiz.
Allah Hafiz, sir. Allah Hafiz, everyone.